Right now, in this very moment, trillions of chemical reactions are happening inside your body. Your cells are breathing, your heart is beating because of tiny molecular exchanges. Your brain is processing these words through chemical signals, crossing gaps smaller than you can imagine. And yet, you feel none of it. This constant, invisible dance has been going on since the moment you were born, and it will continue long after you close your eyes tonight. Chemical reactions are not loud explosions in laboratories. They are the quietest miracles of existence, the gentle conversations between atoms that make life possible. If you find comfort in these quiet scientific truths, please take a moment to like this video and subscribe to the channel so you don't miss more relaxing stories tomorrow. And leave a comment telling me where you're watching from and what time it is there. I love knowing you're out there, settling in for the night. Let's begin with something simple. A chemical reaction is nothing more than atoms rearranging themselves. They form new connections. They break old bonds. They find new partners and create something different than what existed before. It happens everywhere, all the time, in ways so ordinary we forget to notice. Think about a candle burning on your nightstand. The flame looks alive, doesn't it? It flickers and dances. But what you're really watching is a chemical reaction in slow motion. The wax, made of long chains of carbon and hydrogen atoms, meets the heat of the flame. Those atoms break apart from each other. They drift upward as vapor. Then they meet oxygen molecules floating in the air around them. And in that meeting, something beautiful happens. The carbon and hydrogen grab onto the oxygen. They form new partnerships, creating carbon dioxide and water vapor. And in that transformation, they release energy as light and heat. That warm glow touching your face is the result of billions of atoms finding new arrangements, over and over, for as long as the candle burns. This is the fundamental truth of chemistry. Nothing is ever really created or destroyed. Atoms simply change partners. They dance from one arrangement to another. The carbon atoms in that candle wax were once part of ancient plants that lived millions of years ago. Before that, they were carbon dioxide in prehistoric air. Before that, they were part of dying stars. And after your candle burns down, those same carbon atoms will drift out your window, become part of the atmosphere, maybe get absorbed by a tree next spring, become part of a leaf, fall to the ground in autumn, break down in soil, and begin the cycle again. Chemical reactions are patient. They don't rush. Some happen in fractions of a second, like the ones powering the neurons in your brain right now. Others take years, like the slow rusting of iron or the gradual breakdown of rock into soil. But all of them follow the same basic principle. Atoms are constantly seeking stability, looking for the right partnerships, the right arrangements that feel most balanced and calm. Your body understands this rhythm better than your conscious mind ever could. Right now, without any effort from you, millions of chemical reactions are maintaining your existence. Glucose molecules are being broken down to release energy. Oxygen is binding to hemoglobin in your blood. Proteins are being assembled from amino acids. Neurotransmitters are crossing synapses. None of this requires your attention. It simply happens, quietly and perfectly, like a song playing in a language you don't need to understand to feel its beauty. And perhaps that's the most comforting part. You don't have to do anything. The chemistry of life continues, whether you're awake or asleep, whether you're thinking about it or not. These reactions have been perfected over billions of years of evolution. They know what to do. They know how to keep you alive, how to repair damage, how to maintain balance. All you have to do is rest and let them work. As you settle deeper into this moment, your body is already beginning its nighttime chemistry, the reactions that restore and heal, the gentle processes that prepare you for tomorrow. There's a particular kind of chemical reaction that doesn't hurry. It takes its time, years, sometimes decades. You've seen it on old bridges, abandoned cars, forgotten garden tools left out in the rain. Rust, that reddish-brown coating that slowly claims metal surfaces. It looks like decay, like something dying, but really, it's just iron having a very long, very patient conversation with oxygen. When iron meets oxygen in the presence of water, something interesting begins. The iron atoms don't suddenly jump into new arrangements. They don't explode or flash, or make any sound at all. Instead, they start a gradual exchange. An oxygen molecule lands on the iron surface. Water helps facilitate the introduction, and slowly, electron by electron, the iron atoms give up some of their electrons to the oxygen. This creates iron oxide, rust. The transformation happens so slowly, you could watch the same spot every day for a week and see no difference. But come back in a year, and the change becomes obvious. What makes rust so fascinating is how gentle it is. Unlike fire, which is oxidation happening fast, rust is oxidation happening at the pace of patience itself. The iron isn't being destroyed, it's being transformed. Those iron atoms are finding a new form, a new way of existing in the world. They're still there, just arranged differently, bonded to oxygen instead of to each other. In a strange way, rust is iron finding peace with its environment, settling into a more stable state. Think about an old nail left in the garden. Over months and years, that nail slowly grows a coating of rust. The iron at the surface oxidizes first. Then, as water seeps into tiny cracks and pores, the reaction continues deeper. Layer by layer, the metallic iron becomes iron oxide. The nail gets thicker with rust, even as the actual iron beneath diminishes. Eventually, if given enough time, the entire nail could transform completely. What was once shiny and hard becomes crumbly and red. But the atoms themselves haven't gone anywhere. They've just changed partners, formed new bonds, found a different arrangement. This same patient chemistry happens all around us, usually unnoticed. The Statue of Liberty isn't made of iron, it's copper, but it underwent its own slow oxidation over decades. That green coating, called patina, is copper carbonate formed through years of exposure to air and moisture. The copper atoms reacted with oxygen and carbon dioxide, creating a protective layer that's actually prevented further corrosion beneath. What looks like aging is actually preservation, a chemical shield built by time itself. Even the soil beneath your feet is full of oxidized minerals. The red and orange colors in many rocks and clays come from iron oxide. Ancient iron, oxidized over millions of years, giving the earth its warm tones. When you see red desert sand or orange clay, you're looking at rust on a geological scale. Iron that's been patiently transforming since long before humans existed. There's something deeply calming about reactions that happen on these timescales. They remind us that transformation doesn't have to be violent or sudden. Change can be so gradual, it's almost invisible day to day, yet profound when you step back and see the full arc of time. The iron doesn't resist becoming rust. It simply accepts the slow chemistry of its interaction with the world. Your body knows about this kind of patient chemistry too. Right now, without thinking about it, you're participating in one of the most essential chemical reactions of your life. Breathing. Each breath you take is a chemical exchange, a gentle transaction happening millions of times inside your lungs every single day. When you inhale, air flows down into your lungs and reaches tiny structures called alveoli. These are microscopic sacs, so small you could fit millions of them in the space of a grape. Their walls are incredibly thin, just one cell thick, because they need to let molecules pass through easily. On one side of these walls is air, on the other side is blood, and in that narrow space between, oxygen and carbon dioxide trade places through a process so quiet and efficient you never notice it happening. The oxygen molecules in the air you just breathed in are small and light. They slip through the thin walls of the alveoli and into your bloodstream. Once there, they encounter red blood cells, floating by like tiny boats in a river. Each red blood cell contains millions of hemoglobin molecules, and each hemoglobin molecule is perfectly designed to grab onto oxygen. When an oxygen molecule gets close to hemoglobin, something wonderful happens. The oxygen binds to an iron atom at the center of the hemoglobin structure. It's a gentle attachment, strong enough to hold, but loose enough to release later when needed. This binding is a chemical reaction, but not the explosive kind. It's a coordination reaction, where the oxygen molecule forms a temporary partnership with the iron in hemoglobin. The hemoglobin changes color when this happens, shifting from dark red to bright red. This is why blood that's rich in oxygen looks scarlet, while blood that's given up its oxygen appears darker. The color itself is a visual clue to the chemistry happening at a molecular level. Now, your blood carries this oxygen throughout your body. It travels through arteries, reaching every tissue, every cell that needs it. When the hemoglobin arrives at a cell that's running low on oxygen, the bond loosens. The oxygen molecule lets go and slips into the cell, where it will be used to help break down glucose and release energy. This is cellular respiration, another chemical reaction happening constantly. The process that keeps you alive and warm. But the exchange isn't finished. When cells use oxygen to create energy, they produce carbon dioxide as a byproduct. This carbon dioxide needs to leave the cell and get back to the lungs so you can breathe it out. Some of it dissolves directly in blood plasma. Some binds to hemoglobin in different spots than oxygen does. And some reacts with water in your blood to form carbonic acid, which then breaks down into bicarbonate ions. All of this is chemistry, molecules rearranging and finding temporary partnerships to transport waste away from where it's not needed. When this carbon dioxide-rich blood returns to your lungs, the whole process reverses. The carbon dioxide slips out of the blood, crosses those thin alveolar walls, and enters the airspace in your lungs. Then you exhale, and those carbon dioxide molecules leave your body, making room for the fresh oxygen coming in with your next breath. The cycle continues, breath after breath, about 20,000 times a day. And you never have to think about it once. This is the beautiful efficiency of chemistry in living systems. Every breath is a coordinated dance of molecules binding and releasing, moving from high concentration to low concentration, finding equilibrium, maintaining balance. Your body manages this complexity without any conscious input from you, leaving your mind free to rest, to settle, to let go of the day. While your body is busy taking in oxygen and releasing carbon dioxide, plants all around the world are doing the exact opposite. They take in carbon dioxide and release oxygen. It's a perfect exchange, a global balance maintained by chemistry that's been running for billions of years. This process, photosynthesis, might be the most important chemical reaction on Earth. Inside every green leaf, there are millions of tiny structures called chloroplasts. These are like miniature factories, and their job is to capture sunlight and turn it into food. The green color comes from chlorophyll, a molecule that's incredibly good at absorbing light. When a photon of sunlight hits a chlorophyll molecule, it doesn't just bounce off or turn into heat. Instead, it excites an electron in the chlorophyll, bumping it up to a higher energy level. This energized electron is the beginning of everything. That excited electron gets passed along a chain of molecules, like a relay race happening at the molecular level. As it moves, it helps pump hydrogen ions across a membrane, creating a difference in concentration. This difference stores energy, like water building up behind a dam. Eventually, that energy is used to combine carbon dioxide from the air with water from the soil, creating glucose, a simple sugar. The oxygen that was part of the water molecules gets released as a byproduct. It floats out of the leaf and into the air, where animals like us can breathe it in. The beautiful thing about photosynthesis is how it transforms something invisible into something tangible. Carbon dioxide is a gas, weightless and formless. Sunlight is pure energy, nothing you can hold. But combine them with water in the presence of chlorophyll, and you get glucose, a molecule with structure and substance. Plants take that glucose and use it to build everything they are: stems, leaves, roots, flowers, fruits, seeds. All of it started as air and light, transformed through chemistry into solid matter. Think about a tree growing in a forest. Over decades, it might gain tons of mass. Where does all that weight come from? Not from the soil, mostly. The soil provides minerals and water, but the bulk of the tree, the wood and leaves, comes from carbon dioxide pulled out of the air. The tree is literally made of air, transformed by sunlight through chemical reactions happening in every green cell. It's pulling carbon atoms out of the atmosphere and locking them into its structure, one reaction at a time. This same process feeds almost everything alive. Plants use photosynthesis to make glucose, which they use for energy and growth. Animals eat the plants and take in that stored energy. Other animals eat those animals. Every bite of food you've ever taken, every calorie of energy you've ever used, can be traced back to photosynthesis. Back to a moment when sunlight hit a green leaf and started a chain of reactions that eventually led to you, here, now, reading these words. And it's still happening right now, even in darkness. Well, not the light-dependent reactions. Those need sun. But plants are still using the glucose they made during the day, still respiring, still carrying on their chemical existence. During the day, they make more oxygen than they use. At night, they consume oxygen like we do. But over a full day, the balance tips toward oxygen production. One large tree can produce enough oxygen in a year to support 2 people. Forests are Earth's lungs, breathing in carbon dioxide and breathing out oxygen, maintaining the atmosphere that makes our kind of life possible. Photosynthesis is proof that chemistry doesn't have to be complicated to be profound. 6 molecules of carbon dioxide, 6 molecules of water, and light energy combine to make 1 molecule of glucose and 6 molecules of oxygen. It's an elegant equation, simple enough to write on a single line, yet powerful enough to have transformed Earth from a barren rock into a living planet. The glucose that plants make through photosynthesis doesn't stay as glucose forever. When you eat food, that glucose enters your body and becomes fuel. But your cells don't burn it the way a fire burns wood. They break it down carefully, step by step, extracting energy in a controlled process called metabolism. It's like the opposite of photosynthesis, and it's happening inside you right now, even as you rest. Metabolism is sometimes called a slow burn, and that's a perfect description. When you light a match, glucose can react with oxygen explosively, releasing all its energy at once as heat and light. But your cells can't handle that kind of sudden energy release. They need something gentler, more controlled. So instead of one big reaction, metabolism breaks glucose down through a series of smaller reactions, each one releasing just a little bit of energy that the cell can capture and use. This process happens in structures called mitochondria, often called the powerhouses of the cell. Inside these tiny compartments, glucose molecules are taken apart piece by piece. First, the glucose is split into smaller molecules through a process called glycolysis. This happens in the cell's main fluid, outside the mitochondria, and it doesn't even need oxygen. It's an ancient form of energy production, one that evolved billions of years ago, before oxygen was common in Earth's atmosphere. Then those smaller molecules enter the mitochondria, where the real magic happens. In the presence of oxygen, they're broken down even further through a cycle of reactions called the citric acid cycle. Carbon atoms are removed one by one, released as carbon dioxide that eventually makes its way to your lungs and out into the air. The hydrogen atoms are separated too, and their electrons enter another series of reactions called the electron transport chain. This is where most of the energy gets captured. As electrons move through a series of protein molecules in the mitochondrial membrane, they help pump hydrogen ions across that membrane, creating a concentration difference, just like in photosynthesis. That difference stores energy, and when the hydrogen ions flow back through special channels, that energy is used to create ATP, adenosine triphosphate. ATP is like a rechargeable battery for cells. It stores energy in its chemical bonds, and when those bonds break, the energy gets released to power whatever the cell needs to do. Your body makes and uses an astonishing amount of ATP every day. A single cell might recycle its entire ATP supply hundreds of times per day. If you added up all the ATP you create and use in 24 hours, it would weigh about the same as your entire body. But you don't notice any of this happening. It's all chemistry, molecules binding and breaking and rearranging, maintaining the energy flow that keeps you alive and warm. And that warmth is real. Metabolism doesn't capture all the energy from glucose perfectly. Some of it escapes as heat, and that's not a failure, it's a feature. That heat keeps your body at a steady temperature, around 37 degrees Celsius. Even when you're sleeping, even when you're perfectly still, your metabolism is generating warmth. It's why you need blankets on cold nights, and why you can feel your own body heat when you press your hands together. Think about that for a moment. The warmth you feel right now, the temperature of your skin, comes from millions of tiny chemical reactions happening in your cells. Glucose from the food you ate hours or days ago is being broken down. Oxygen you breathed in minutes ago is being used. and the result is energy and carbon dioxide and water and heat. You are kept alive by controlled burning, by chemistry that knows exactly how fast to go, how much energy to release, how to maintain balance without ever needing your conscious input. Not all organisms break down glucose the same way your cells do. Some don't use oxygen at all. They rely on an older, simpler process called fermentation. It's less efficient than metabolism with oxygen, but it's been working for billions of years, and humans have learned to harness it to create some of the most beloved foods and drinks in history. Fermentation is what happens when yeast or bacteria break down sugars in the absence of oxygen. Instead of fully breaking glucose down into carbon dioxide and water, fermentation stops partway through, creating other products. When yeast ferments grape juice, it produces alcohol and carbon dioxide. When bacteria ferment milk, they produce lactic acid. The specific products depend on the organism doing the fermenting, but the basic principle is the same. Sugars get partially broken down, releasing some energy and creating byproducts that change the flavor, texture, and preservation of food. Think about bread rising in a warm kitchen. The yeast in the dough is alive, consuming the sugars in the flour and releasing carbon dioxide gas. Those tiny bubbles get trapped in the gluten network, making the dough expand and become light and airy. The small amount of alcohol produced evaporates when the bread bakes. What you're left with is the transformed result of millions of yeast cells quietly fermenting, doing their ancient chemistry in the darkness of the dough. Wine happens the same way, just without the baking. Grapes are crushed, yeast is added or naturally present on the grape skins, and fermentation begins. Over days or weeks, the yeast consumes the sugar in the grape juice, converting it into alcohol. The process is slow and careful. If it goes too fast, the wine becomes harsh. If the temperature isn't right, the fermentation might stop before all the sugar is consumed, or unwanted bacteria might take over. Winemakers have spent centuries learning how to manage this process, but ultimately, they're just creating the conditions for chemistry to happen. The yeast does the actual work. The same principle applies to cheese. Bacteria are added to milk, and they begin consuming lactose, the sugar in milk, producing lactic acid as a byproduct. This acid causes the milk proteins to clump together and separate from the liquid whey. Different bacteria produce different acids and enzymes, which is why there are thousands of varieties of cheese, each with its own flavor and texture. Some cheeses age for months or years, during which additional chemical reactions continue, breaking down proteins and fats, developing complex flavors that weren't there at the start. Fermentation is also happening in your own body right now. When your muscles work harder than your blood can supply oxygen, they switch to a form of fermentation to keep producing energy. They break down glucose without oxygen, creating lactic acid as a byproduct. This is what causes that burning sensation when you exercise intensely. The lactic acid builds up faster than your blood can carry it away. But it's not harmful, just temporary. Once you rest and catch your breath, your body clears the lactic acid, and your muscles recover. Cultures around the world have used fermentation for thousands of years to preserve food. Without refrigeration, fresh milk spoils quickly, but fermented milk becomes yogurt or kefir, which lasts much longer. Fresh cabbage wilts and rots, but fermented cabbage becomes sauerkraut or kimchi, preserved by the acids produced during fermentation. Soybeans become miso and tempeh, Cucumbers become pickles. All through the patient work of bacteria and yeast, transforming sugars into acids and other compounds that both preserve the food and create entirely new flavors. There's something satisfying about fermentation. It's chemistry you can see and taste and smell. It happens slowly enough that you can track its progress. The bubbling of fermenting beer, the tang of sourdough starter, the way yogurt thickens over hours. These are chemical reactions made tangible, transformations happening at human speed, turning simple ingredients into something more complex and delicious. Let's stay with bread for a moment longer, because what happens in a loaf of bread as it bakes is a perfect example of how multiple chemical reactions can work together to transform simple ingredients into something entirely new. Flour, water, yeast, salt. 4 basic ingredients, but the chemistry they undergo together is remarkably complex. When you mix flour and water, proteins in the flour, called glutenin and gliadin, absorb the water and stick together, forming gluten. Gluten is what gives bread dough its stretchy, elastic quality. It creates a network of protein strands that can trap gas bubbles. As you knead the dough, you're helping those proteins align and strengthen their bonds, building a structure that will hold the bread together as it rises and bakes. The yeast you added is busy fermenting, breaking down the starches in flour into simpler sugars, and then converting those sugars into carbon dioxide and a small amount of alcohol. The carbon dioxide gets trapped in the gluten network, forming thousands of tiny bubbles. This is what makes the dough rise. Leave it in a warm place for an hour, and you'll come back to find it's doubled in size, light and puffy, full of trapped gas from the yeast's patient work. But the real transformation happens in the oven. When you put the dough in to bake, the heat triggers a cascade of chemical reactions. First, the yeast, which has been happily fermenting, suddenly finds itself in an environment too hot to survive. But before it dies, the heat causes it to work even faster for a brief moment, releasing a final burst of carbon dioxide. This is called oven spring, when the bread expands rapidly in the first few minutes of baking. As the temperature inside the dough rises, other reactions begin. The starches in the flour start to gelatinize, absorbing water and swelling. The proteins denature, meaning they unfold and form new bonds with each other, solidifying the structure. The alcohol produced by fermentation evaporates, creating more of those lovely air pockets. Water vapor forms and tries to escape, contributing to the bread's texture. Around the outside, where the heat is most intense, the Maillard reaction begins. This is one of the most important reactions in all of cooking. It's what happens when proteins and sugars are heated together. They break apart and recombine in hundreds of different ways, creating new molecules that are responsible for the brown color and rich, complex flavors of crusts on bread, seared meat, roasted coffee, and countless other foods. The Maillard reaction is why toast tastes different than raw bread, why a seared steak tastes better than a boiled one. At the same time, caramelization might be happening on the crust if any sugars are present on the surface. Caramelization is different from the Maillard reaction. It only involves sugars, no proteins, and it happens at higher temperatures. When sugar molecules get hot enough, they break apart and reform into new compounds that are brown and taste sweet and slightly bitter, like caramel. In bread, this adds another layer of flavor and color to the crust. Inside the loaf, the temperature is rising too, but not as fast. The crumb, the soft interior of the bread, doesn't get hot enough for the Maillard reaction or caramelization. Instead, it's going through its own changes. The starches finish gelatinizing, becoming soft and tender. The gluten network sets in place, creating that characteristic texture of good bread, soft but with structure, airy but not falling apart. When you finally take the bread out of the oven, the reactions don't immediately stop. The crust is still hot, still crackling as it cools and releases steam. The crumb is setting as it comes down to room temperature. Even hours later, the bread is still changing. Starches slowly recrystallize, which is part of why bread gets stale. It's not drying out. It's the starch molecules arranging themselves differently, becoming firmer and less appealing to eat. But while it's fresh, while it's warm, you're tasting the result of dozens of chemical reactions, all working together in perfect timing to turn flour and water into something delicious. All these reactions we've explored involve molecules changing partners, breaking bonds, forming new ones. But there's a particular type of reaction that has a special kind of elegance. It's called neutralization, and it happens when acids and bases meet and cancel each other out, creating something entirely neutral and peaceful. Acids are substances that donate hydrogen ions when dissolved in water. Bases are substances that accept hydrogen ions or donate hydroxide ions. They're chemical opposites. Acids taste sour, like lemon juice or vinegar. Bases taste bitter and feel slippery, like soap. Strong acids can burn your skin by breaking down proteins. Strong bases can do the same damage. But when you mix an acid and a base together in the right proportions, something remarkable happens. They neutralize each other, forming salt and water. The reaction is surprisingly simple. Take hydrochloric acid, which is strong and corrosive, used in industrial cleaning and produced naturally in your stomach. Mix it with sodium hydroxide, a base so caustic it's used to unclog drains. When these two dangerous chemicals meet, the hydrogen ions from the acid combine with the hydroxide ions from the base, creating water. The sodium from the base pairs up with the chloride from the acid, creating sodium chloride. Table salt, the same thing you sprinkle on your food. This transformation from dangerous to harmless is one of the most satisfying things in chemistry. It's like watching two opposing forces find balance, reaching a middle ground where neither dominates. The resulting solution is neither acidic nor basic. It's neutral, usually with a pH right around 7. The reaction releases heat too, because forming those new bonds releases energy that was stored in the original molecules. Your body uses neutralization constantly. The food you eat gets broken down in your stomach with the help of hydrochloric acid, strong enough to dissolve metal. But when that acidic mixture moves into your small intestine, it would damage the delicate tissues there if it stayed acidic. So, your pancreas releases bicarbonate, a base, which neutralizes the acid before it can cause harm. This happens automatically, a chemical balancing act your body performs with every meal. Neutralization is also why antacids work. When your stomach produces too much acid, you might feel heartburn or indigestion. Antacids contain bases like calcium carbonate or magnesium hydroxide. When you swallow them, they react with the excess acid in your stomach, neutralizing it and bringing your stomach contents closer to neutral. The chemical reaction is the same one that happens in a lab, just scaled down and happening inside you. In nature, neutralization helps maintain the balance of ecosystems. When rainwater, which is slightly acidic, because it absorbs carbon dioxide from the air, falls on limestone or chalk, which are basic, a neutralization reaction occurs. The acid in the rain reacts with the calcium carbonate in the rock, slowly dissolving it, but also neutralizing the acid. This is why caves form in limestone regions. It's a neutralization reaction that's been going on for thousands or millions of years, carving out underground chambers one molecule at a time. Farmers use neutralization to improve their soil. If soil becomes too acidic for the crops they want to grow, they add lime, which is calcium oxide or calcium hydroxide, both bases. The lime reacts with the acids in the soil, neutralizing them and bringing the pH closer to neutral. This makes nutrients more available to plants and creates better growing conditions. It's applied chemistry, using neutralization reactions to solve practical problems. There's something almost philosophical about neutralization. Two extremes meeting and finding middle ground. Opposition transformed into harmony. Danger converted into safety. It's a reminder that balance is possible, that even the most reactive substances can find peace when they encounter their complement. The reaction is fast, sometimes instant, but the result is stable and lasting. Some chemical reactions happen so gently, so gradually, that they look like weather. The formation of clouds, for example, is essentially a physical and chemical process involving water molecules changing state, gathering together, becoming visible where moments before there was only clear air. It's a transformation that happens constantly, all around the planet, in the sky above you right now. Water is everywhere on Earth, in the oceans, lakes, and rivers, obviously, but also in the air, invisible as vapor. When the sun warms a body of water, some of the molecules at the surface gain enough energy to break free from the liquid and float up into the air as gas. This is evaporation. The water molecules spread out through the atmosphere, bouncing around, carried by air currents, completely invisible because they're individual molecules, mixed in with nitrogen and oxygen. But warm air can hold more water vapor than cold air. As the air rises, it expands and cools. Eventually, it reaches a point where it can't hold all that water vapor anymore. The air becomes saturated. When that happens, the water vapor needs to condense, to change back from gas to liquid. But water molecules don't just spontaneously form droplets in midair. They need something to condense onto. They need tiny particles, like dust, sea salt, or pollution particles. These are called condensation nuclei, and they're floating everywhere in the atmosphere. When a water molecule bumps into one of these tiny particles, it sticks. Then another water molecule bumps into it and sticks. Then another and another. Slowly, a microscopic droplet forms. Millions of these droplets form at the same time, all around the same altitude where the temperature and humidity are right. And suddenly, what was invisible becomes visible. A cloud appears, made of countless tiny water droplets, each one too small to fall, suspended in the air, reflecting sunlight, creating those soft shapes we see drifting across the sky. The formation of each droplet is both a physical change and involves molecular interactions. When water molecules come together to form liquid from vapor, they're releasing energy. The bonds between water molecules in liquid are stronger than in gas, and forming those bonds releases heat. This is called the latent heat of condensation. It's the same amount of energy that was absorbed when the water evaporated in the first place, now being released back into the air. This is why storm systems have so much energy. The condensation of water vapor releases enormous amounts of heat into the atmosphere, powering winds and rain, and sometimes even tornadoes. Not all clouds are the same, and that's because conditions at different altitudes are different. Low clouds form where it's relatively warm, so the water droplets stay liquid. High clouds form where it's so cold that water vapor doesn't even condense into liquid droplets. Instead, it goes directly from gas to solid ice crystals, a process called deposition. Those high, wispy cirrus clouds you sometimes see are made entirely of ice, tiny crystals catching the light, sometimes creating halos around the sun or moon. When the droplets in a cloud grow large enough, they start to fall. If the air below is dry, they might evaporate before reaching the ground. But if the air is humid all the way down, they make it to the surface as rain. Each raindrop is a collection of millions of cloud droplets that bumped into each other and merged, growing heavy enough to overcome the air resistance holding them up. And when those raindrops hit the ground, they complete the cycle. The water seeps into soil, flows into streams, makes its way back to the ocean, and eventually evaporates again, returning to the atmosphere to form new clouds. This cycle has been running for billions of years. The same water molecules have been evaporating and condensing and falling as rain over and over again. The water you drank today might have fallen as rain last week, or last year, or 1,000 years ago. It might have been part of an ancient ocean, absorbed by a dinosaur, locked in ice for millennia, released and cycled through the atmosphere countless times. And right now, some of it is up there, invisible vapor in the air, waiting for the right conditions to gather together and become visible as a cloud. While clouds reflect light from the sun, some creatures make their own light through chemistry. It's called bioluminescence, and it's one of the most enchanting chemical reactions in nature. No heat, no fire, just a soft glow produced by living organisms through a reaction that's been perfected over millions of years of evolution. The basic chemistry of bioluminescence is surprisingly similar across different species. It involves a molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it produces light. That's the simple version. The complex version involves the luciferin molecule getting oxidized, meaning it combines with oxygen and loses electrons in the process. This creates an excited state molecule that quickly releases its extra energy as a photon of light. Then the cycle can begin again with new luciferin molecules. What makes this reaction special is how efficient it is. When you burn something to produce light, like a candle or a light bulb, most of the energy gets wasted as heat. That's why light bulbs get hot, and why fires are dangerous to touch. But bioluminescence is what scientists call cold light. Nearly 100% of the energy from the chemical reaction gets converted into light, with almost no heat produced. It's one of the most efficient reactions known, far better than any technology humans have invented. Fireflies are probably the most familiar bioluminescent creatures. On summer evenings, they flash their lights in patterns, each species with its own unique rhythm. The males fly around flashing, trying to attract females. The females sit on leaves or grass and flash back if they're interested. It's all communication through chemistry. The firefly controls when to produce light by controlling the oxygen supply to the light-producing cells. When it wants to flash, it opens up airways that deliver oxygen to the luciferin, and the reaction happens. producing that yellow-green glow that lasts a few seconds before fading. In the ocean, bioluminescence is even more common. Some estimates suggest that up to 90% of deep-sea creatures produce light in some way. Down where sunlight never reaches, bioluminescence becomes the primary form of light. Some fish use it to attract prey, dangling a glowing lure in front of their mouths. Others use it as camouflage, producing light on their undersides that matches the faint light filtering down from above, hiding their silhouettes from predators below. Some use it to communicate, flashing patterns to find mates or warn others of danger. One of the most beautiful displays happens in certain coastal waters, where tiny organisms called dinoflagellates produce flashes of blue light when disturbed. Swim through water filled with these creatures at night, and every movement of your hand creates a trail of glowing sparkles. Waves breaking on the shore light up with blue fire. It looks magical, but it's just chemistry. The dinoflagellates produce the light as a defense mechanism, possibly to startle predators or attract even larger predators that might eat whatever is disturbing them. Some squid and octopuses have bacteria living in special organs in their bodies. These bacteria are bioluminescent, and they provide light for the host in exchange for nutrients and a safe place to live. It's a partnership, a symbiotic relationship where both species benefit. The squid uses the bacterial light for camouflage or communication, and the bacteria get everything they need to survive. The chemical reaction happens inside the bacterial cells, the same luciferin and luciferase reaction, producing a steady glow that the squid can control by covering or uncovering the light organ. Even on land, there are organisms besides fireflies that produce light. Certain fungi glow in the dark, usually a soft green light barely bright enough to see. They grow on rotting wood, and the glow might help attract insects that spread their spores. The chemistry is similar, a luciferin-type molecule reacting with oxygen, though the specific molecules are different from those in fireflies or marine creatures. The fact that bioluminescence evolved independently in so many different groups of organisms suggests it's a useful trait, worth the energy investment required to maintain the chemical machinery that produces light. There's something deeply peaceful about watching bioluminescence. Maybe it's because the light is so gentle, so different from the harsh, artificial lights we're used to. Or maybe it's knowing that what you're seeing is living chemistry, creatures using reactions to communicate, to hunt, to defend themselves, to find each other in the darkness. That gentle glow of bioluminescent creatures reminds us that beauty in chemistry often comes from simplicity and pattern, and perhaps no chemical process creates more delicate patterns than the formation of snowflakes, each one a unique crystal grown from water vapor in the cold upper atmosphere, each one following the same basic rules, yet emerging completely individual. Snowflakes begin as tiny particles, just like clouds do. But instead of forming liquid droplets, the water vapor in freezing air deposits directly onto the particle as ice, skipping the liquid phase entirely. This happens when the air is below freezing and saturated with moisture. A water molecule bumps into the cold particle and sticks. Then another arrives and sticks to the first. The way they attach follows rules determined by the molecular structure of ice. Water molecules are shaped like a wide V, with the oxygen atom at the point and the two hydrogen atoms forming the arms. When water freezes, These V-shaped molecules arrange themselves in a hexagonal pattern, six-sided, because that's the most stable configuration given the angles of the hydrogen bonds between molecules. This hexagonal structure is why all snowflakes have six sides or six branches. It's not random, it's chemistry, the natural result of how water molecules prefer to bond when they're solid. As the tiny ice crystal falls through the cloud, it encounters different conditions. Sometimes the air is colder, sometimes slightly warmer. Sometimes there's more moisture, sometimes less. Each of these conditions affects how new water molecules attach to the growing crystal. In very cold, dry air, the crystal might grow slowly, forming simple shapes. In warmer, wetter conditions, it might grow faster, developing elaborate branches and side branches, creating those complex fern-like patterns we associate with snowflakes. The remarkable thing is that all six arms of a snowflake experience the same conditions at the same time as the crystal falls. So they all grow in the same way, creating symmetry. The six branches might develop intricate, identical patterns because they're all responding to the same sequence of temperature and humidity changes. But because each snowflake takes its own unique path through the cloud, encountering its own specific series of conditions, no two snowflakes are exactly alike. Each one is a record of its journey, its structure determined by the particular chemistry it experienced during growth. Some snowflakes are simple hexagonal plates, flat and basic. Others are stellar dendrites, with six elaborate branches spreading out like stars. Some are needles, long and thin. Others are columns or prisms. The variety is endless, but they all share that six-fold symmetry, all built from the same water molecules following the same bonding rules. The differences come from the environmental conditions during growth, the temperature and humidity at each moment of formation. When snowflakes reach the ground, they don't stay perfect for long. They start to sublime, going from solid back to vapor, especially on sunny days. Or they melt, returning to liquid. The elaborate structures collapse as the bonds between molecules break, but for a brief time, they exist as tiny frozen sculptures, each one a testament to the beauty that emerges when simple molecules follow simple rules in response to changing conditions. Pick up a snowflake on a cold day and look closely before it melts, and you're seeing crystallography in action, molecular architecture on a scale you can observe with your own eyes. While snowflakes demonstrate how structure emerges from simple molecular rules, your body contains its own chemical laboratories where complex molecules are systematically taken apart. Digestion is happening inside you right now, breaking down the food you ate hours ago into simpler molecules your cells can use. It's a series of chemical reactions so well coordinated, so precisely timed, that you never have to think about it at all. Digestion begins the moment food enters your mouth. Your saliva contains an enzyme called amylase, which starts breaking down starches into simpler sugars. Starches are long chains of glucose molecules bonded together, and amylase cuts those chains into shorter pieces. You can feel this happening if you chew a piece of bread for a long time. It starts to taste sweeter as the starch gets converted to sugar. This is enzyme catalysis, where a protein speeds up a chemical reaction that would otherwise take far too long to be useful. When you swallow, the food travels down to your stomach, where it meets hydrochloric acid. Your stomach produces this strong acid to help break down proteins and kill bacteria that might have come in with your food. The acid alone isn't enough though. Your stomach also releases an enzyme called pepsin, which specifically targets the bonds between amino acids in protein molecules. Pepsin works best in very acidic conditions, which is why your stomach maintains such a low pH. Together, the acid and enzyme begin breaking proteins into smaller fragments. The stomach churns and mixes, turning food into a thick liquid called chyme. This takes hours, depending on what you ate. Fatty foods take longer because fat molecules are harder to break down than carbohydrates or proteins. Eventually, small amounts of chyme get released into your small intestine, where most of the real work of digestion happens. Your pancreas releases enzymes into the small intestine. Lipases break down fats into fatty acids and glycerol. Proteases continue breaking down proteins into individual amino acids. Amylases finish converting starches into simple sugars. Each enzyme is specific, targeting certain types of bonds, catalyzing reactions that would be impossibly slow without their help. This is the beauty of biological catalysis. Enzymes don't force reactions to happen. They just make it much easier for reactions to occur that want to happen anyway. At the same time, your liver produces bile, which helps with fat digestion. Bile isn't an enzyme. It's a mixture of molecules that act like soap, breaking large fat droplets into smaller ones. This emulsification increases the surface area of the fat, giving lipase enzymes more places to work. It's a physical and chemical process working together, making the chemistry more efficient. The walls of your small intestine are lined with tiny finger-like projections called villi, and each villus is covered in even tinier projections called microvilli. This creates an enormous surface area for absorption. As food molecules get broken down into their simplest forms, glucose, amino acids, fatty acids, vitamins, minerals, they pass through the intestinal wall and into your bloodstream. From there, they travel to cells throughout your body to be used for energy, growth, and repair. What's left after all the useful nutrients are absorbed moves into your large intestine. Here, water gets reabsorbed into your body, and bacteria help break down any remaining material. These bacteria are doing their own chemistry, fermenting fibers and producing vitamins like vitamin K and some B vitamins as byproducts. You don't even produce these vitamins yourself. You rely on the chemistry of bacteria living in your gut. All of this happens automatically while you sleep, while you work, while you rest. Your digestive system is always active, always processing, always breaking down complex molecules into simpler ones through carefully orchestrated chemical reactions. Millions of enzyme molecules working simultaneously, each one speeding up its particular reaction thousands or millions of times, turning food into fuel without you having to direct any of it consciously. Just as your body breaks down molecules it no longer needs, trees do something similar each autumn. They dismantle the green chlorophyll in their leaves, breaking it down and retrieving valuable nutrients before the leaves fall. What's left behind is a display of colours that's been happening every autumn for millions of years, a chemical transformation that marks the changing of seasons. During spring and summer, leaves are packed with chlorophyll. This is the molecule that captures sunlight for photosynthesis, and it's intensely green, so green that it masks other colours that are also present in the leaf. Those other pigments are there all along, but you can't see them because the chlorophyll overwhelms them. Yellow pigments called xanthophylls and orange pigments called carotenes are in the leaf from the beginning, helping capture different wavelengths of light to support photosynthesis. As days get shorter and temperatures drop, the tree begins preparing for winter. It starts forming a layer of cells at the base of each leaf stem, a barrier that will eventually seal off the leaf completely. This cuts off the supply of water and nutrients to the leaf. Without fresh supplies, the leaf can't maintain its chlorophyll anymore. The chlorophyll molecules start to break down, and the tree carefully retrieves the nitrogen and other nutrients from them, moving those valuable resources back into the branches and trunk, where they'll be stored for winter. As the green chlorophyll disappears, the yellow and orange pigments that were always there become visible. They were hidden before, but now they shine through. This is why many leaves turn yellow or gold in autumn. It's not that the tree is creating new colours, it's revealing colours that were masked. The chemical structure of these pigments is different from chlorophyll. They're more stable, less sensitive to cold, so they remain intact even as the chlorophyll breaks down. Some trees produce additional colours in autumn. Red and purple hues come from pigments called anthocyanins, which are actually synthesized in the fall in response to bright light and cold nights. When a leaf is exposed to sun during the day but experiences cold temperatures at night, sugars get trapped in the leaf as that barrier layer forms. In the presence of these sugars and bright light, the leaf produces anthocyanins. These pigments act as a kind of sunscreen, protecting the leaf from damage as it breaks down its other components and retrieves nutrients. The intensity of fall colours varies from year to year depending on weather conditions. The best autumn displays happen when there are warm, sunny days and cool, but not freezing nights. These conditions promote anthocyanin production and slow the breakdown of other pigments, creating those vivid reds and purples alongside the yellows and oranges. If the weather stays too warm, or if an early freeze hits, the colours might be less impressive because the chemistry doesn't have time to fully develop. Eventually, the barrier layer at the base of the leaf stem completes its formation. The connection weakens and the leaf falls. On the ground, other chemical reactions take over. Fungi and bacteria begin breaking down the leaf material, decomposing it back into simpler compounds that enrich the soil. The carbon, nitrogen, and minerals that made up the leaf get recycled, becoming available for new growth when spring returns. Nothing is wasted. Everything transforms into something else. There's a quiet melancholy to autumn leaves, but also a kind of beauty in the efficiency of it all. The tree isn't dying, it's adapting, preparing for winter by shutting down what it doesn't need and conserving what it does. The colours are a side effect of careful chemistry, the tree's way of managing its resources and protecting itself during the transition. And each falling leaf is a reminder that change is natural, that letting go is sometimes the wisest response to shifting conditions. Trees take months to prepare for winter, slowly dismantling chlorophyll and sealing off leaves. Concrete works on a similar timescale, but in reverse. Instead of breaking down, it's building up, forming new bonds, gaining strength through a chemical process that takes weeks to complete and continues at a slower pace for years afterward. This is called curing, and it's one of the most important chemical reactions in construction. When you mix cement powder with water, you're starting a complex series of reactions called hydration. Cement is made mostly of calcium silicates, compounds of calcium, silicon, and oxygen that were created by heating limestone and clay to extreme temperatures. These calcium silicates are reactive, waiting for water to unlock their potential. When water arrives, the calcium silicates start to dissolve, just slightly, and the calcium and silicate ions begin forming new compounds with the water molecules. The main product of this reaction is calcium silicate hydrate, often just called CSH. This is a gel-like substance that forms around the cement particles, binding them together. As more CSH forms, it creates an interlocking network of crystals that grows stronger over time. Another product is calcium hydroxide, which fills spaces between particles and contributes to the overall structure. These reactions are exothermic, meaning they release heat. That's why fresh concrete feels warm to the touch, even without any external heating. The process is slow and patient. Within a few hours, the concrete begins to set, meaning it's no longer fluid, but still not strong. After about a day, it's hard enough to walk on, though still vulnerable. After a week, it's reached most of its design strength. But the reactions don't stop there. They continue for weeks, months, even years, though at an ever slower rate. Concrete tested after 28 days might be only 80% as strong as the same concrete tested after a year. The chemistry keeps going, slowly adding strength, slowly filling in microscopic gaps with new crystals. Water is essential to this process, not just for mixing, but for continued curing. If concrete dries out too fast, the reactions stop before they're complete, and the concrete ends up weaker than it should be. This is why construction workers sometimes spray fresh concrete with water, or cover it with plastic sheeting to keep moisture in. The goal is to keep the reactions going at a steady pace, giving the CSH network time to fully develop. Temperature matters too. The reactions happen faster when it's warm and slower when it's cold. In winter, concrete might need weeks to reach the strength it would achieve in days during summer. In very cold conditions, water in the concrete can freeze before the reactions are complete, which can damage the structure. This is why contractors sometimes use heaters or insulating blankets to protect fresh concrete in cold weather. The beauty of concrete is in its transformation from a flowing liquid to a stone-like solid, all through chemistry. No heat is applied, no external energy is needed beyond the initial mixing. The cement and water react, forming new compounds that interlock and harden, creating a material that can support enormous loads. Bridges, buildings, roads, dams, all of them rely on this slow chemical process, on the patient formation of calcium silicate hydrate crystals that bind sand and gravel into a cohesive whole. And even after the concrete is in service, carrying loads, exposed to weather, the chemistry continues. Very slowly, the concrete reacts with carbon dioxide from the air in a process called carbonation. The calcium hydroxide in the concrete reacts with CO2 to form calcium carbonate, which is actually slightly stronger than calcium hydroxide. This gradual carbonation is part of why ancient Roman concrete structures are still standing 2,000 years later. The chemistry never truly stops. It just slows down to a pace measured in decades and centuries. Still working, still gradually changing, still responding to its environment through molecular interactions. Concrete hardens over weeks through patient chemistry, gaining strength as new bonds form. Fruit undergoes its own transformation, but with the opposite goal. Instead of getting harder, it gets softer. Instead of becoming more stable, it becomes ready to decay. Ripening is a carefully controlled chemical process that makes fruit sweeter, softer, and more appealing to eat, all timed perfectly to help the plant spread its seeds. The trigger for ripening in many fruits is a simple gas called ethylene. It's a hormone, just 2 carbon atoms bonded together with 4 hydrogen atoms attached. Plants produce ethylene naturally, and when fruit cells detect it, they activate a cascade of chemical reactions that transform the fruit from hard and sour to soft and sweet. This is why putting a ripe banana next to unripe fruit makes everything ripen faster. The banana is releasing ethylene gas, and the nearby fruit responds to it. One of the first things that happens during ripening is the breakdown of chlorophyll, just like in autumn leaves. Green fruit contains chlorophyll that masks other colours. As the chlorophyll breaks down, the underlying colours emerge. Yellow in bananas, red in tomatoes and strawberries, orange in oranges. These colours often signal to animals that the fruit is ready to eat, a visual advertisement created through chemistry. At the same time, the cell walls in the fruit begin to break down. Fruit cell walls are held together by a substance called pectin, which is a complex carbohydrate. During ripening, enzymes called pectinases start cutting the bonds in pectin, weakening the cell wall structure. This is what makes ripe fruit soft. A green banana is firm because its cell walls are intact. A ripe banana is soft because those walls have been partially dissolved. If you let it go too far, the banana becomes mushy as the cell walls break down completely. Starches in the fruit also get converted to sugars. Unripe fruit contains long chains of starch molecules that don't taste sweet. During ripening, enzymes break these chains down into glucose and fructose, simple sugars that taste much sweeter. This is why ripe fruit is so much more pleasant to eat than unripe fruit. The chemical composition is different, and your taste buds respond to that difference. A green banana is mostly starch, a ripe banana is mostly sugar, and the transformation happens through enzyme activity triggered by ethylene. Acids in the fruit decrease as well, though not always by much. Some fruits remain tart even when ripe, like citrus fruits and some berries. But, in general, the balance shifts towards sweetness as organic acids get metabolized or converted into other compounds. The combination of increased sugar and decreased acid creates the flavor profile we associate with ripe fruit. The texture changes too, not just from pectin breakdown, but from changes in the cell contents. Ripe fruit cells are full of juice, their vacuoles swollen with water and dissolved sugars. When you bite into a ripe peach or plum, cells rupture easily, releasing all that sweet liquid. In unripe fruit, the cells are more rigid and less juicy, making the eating experience less satisfying. Different fruits ripen at different rates. Bananas and avocados continue ripening after they're picked because they produce their own ethylene. These are called climacteric fruits. Others, like strawberries and grapes, don't ripen further once picked because they don't produce enough ethylene to trigger the process. They're called non-climacteric fruits. This is why you should pick berries when they're already ripe. But you can pick bananas when they're green and let them ripen on your counter. The timing of ripening is crucial for the plant. If fruit ripens too early, the seeds inside might not be mature enough to grow. If it ripens too late, the fruit might fall and rot before any animals find it and eat it. The ethylene-triggered ripening system allows the plant to control this timing precisely, ensuring the fruit becomes appealing to eat exactly when the seeds are ready to be spread. It's chemistry in service of reproduction, a transformation that benefits both the plant and the animals that eat its fruit, just as ethylene triggers lasting changes in fruit, making them permanently softer and sweeter. Your brain uses chemistry to create lasting changes that we call memories. Every experience you have, every thought you think, every skill you learn is encoded through chemical reactions that alter the connections between neurons. Memory is physical, molecular, built from the same basic chemistry that governs everything else in your body. When you experience something, neurons in your brain fire in specific patterns. A neuron sending a signal releases molecules called neurotransmitters from the end of its branch into the tiny gap between it and the next neuron. This gap is called a synapse, and it's where most of the important chemistry happens. The neurotransmitters float across the gap and bind to receptors on the receiving neuron, triggering it to fire as well. This happens in milliseconds, a chain of chemical signals passing from neuron to neuron, creating the patterns that represent thoughts and perceptions. But if memory was just neurotransmitters crossing synapses, it would disappear as soon as the neurotransmitters got cleared away, which happens almost immediately. For memory to last, something more permanent has to change. This is where a process called long-term potentiation comes in. When a particular path between neurons gets used repeatedly, the connection gets stronger. More receptors appear on the receiving neuron. The sending neuron releases more neurotransmitter. The gap might even get physically smaller, making transmission more efficient. These changes involve genes turning on and new proteins being made. The neuron essentially rebuilds itself, modifying its structure in response to activity. This is happening inside your neurons right now, as you process these words, as your brain decides what's important enough to remember. Some synapses are getting stronger, others are getting weaker. The physical structure of your brain is changing, molecule by molecule, in response to your experiences. The process requires several specific neurotransmitters. Glutamate is the main excitatory neurotransmitter, the one that makes neurons more likely to fire. When glutamate binds to certain receptors, called NMDA receptors, it allows calcium ions to flow into the receiving neuron. This calcium influx is a signal that something important is happening, that this connection should be strengthened. The calcium triggers a cascade of reactions inside the cell, activating enzymes that modify existing proteins and turn on genes to make new ones. Another important molecule is CREB, a protein that acts as a switch for memory-related genes. When activated by calcium and other signals, CREB binds to DNA and turns on genes involved in making the structural changes needed for long-term memory. Without CREB, short-term memories can form, but they don't become permanent. The chemistry is there for immediate recall, but not for lasting storage. Different types of memories involve different brain regions and slightly different chemistry. Emotional memories, the kind that feel vivid and powerful, involve the amygdala and are strengthened by stress hormones like adrenaline and cortisol. These hormones enhance the chemical signals that tell neurons to encode the experience strongly. This is why you remember emotionally charged events more clearly than mundane ones. The chemistry is literally different, amplified by hormones that tell your brain this experience matters. Sleep is crucial for memory consolidation, which is another reason to rest. During sleep, especially deep sleep, your brain replays patterns of activity from the day, strengthening the important connections and weakening others. The chemistry of learning continues even when you're unconscious, your brain sorting through what to keep and what to let fade. all through the same processes of synaptic strengthening and weakening. Forgetting is also chemistry. Memories fade when synapses weaken, when proteins break down, when connections get pruned away to make room for new information. Your brain can't strengthen every connection, so it has to be selective. The memories that matter, the ones you use and rehearse, stay strong. The ones you don't need gradually dissolve, the proteins that maintained them recycled for other purposes. Even forgetting is an active process, not just passive decay, but deliberate chemical dismantling of connections that are no longer useful. Your brain stores memories through chemistry that can last a lifetime, encoding experiences in molecular form. The ocean does something similar on a much larger scale, storing carbon dioxide from the atmosphere through chemical reactions that can lock it away for thousands of years. This is part of the global carbon cycle, a planetary memory system written in molecules dissolved in seawater and embedded in shells and rocks on the ocean floor. When carbon dioxide from the air touches the ocean surface, some of it dissolves. This is a simple physical process at first, gas molecules slipping into the water. But once dissolved, the CO2 doesn't just stay as CO2. It reacts with water molecules to form carbonic acid, a weak acid that immediately splits apart into hydrogen ions and bicarbonate ions. This happens in every ocean, all the time, a constant chemical reaction at the interface between air and sea. The carbonic acid makes seawater slightly acidic, though not nearly as acidic as something like vinegar. Ocean pH is around 8, which is still basic on the pH scale, but it's more acidic than it would be without all that dissolved CO2. As atmospheric CO2 levels increase, the ocean absorbs more of it, and the pH drops slowly. This process, called ocean acidification, is happening now, measurable year by year, a direct chemical consequence of more CO2 in the air. The bicarbonate ions formed from CO2 don't just stay dissolved forever. Many marine organisms use them to build their shells and skeletons. Corals, mollusks, sea urchins, microscopic plankton, all of them take calcium ions from seawater and combine them with carbonate ions, which come from the bicarbonate to make calcium carbonate. This is the same compound that makes up limestone and chalk. When these organisms die, their shells sink to the ocean floor, carrying carbon with them. Over geological time, massive amounts of carbon get locked into sediments this way. The shells accumulate, layer upon layer, eventually forming limestone rock. This carbon is effectively removed from the active carbon cycle, stored in solid form for millions of years, unless the rock gets uplifted and weathered by rain, releasing the carbon back into circulation. It's an incredibly slow process, but it's one of the main ways Earth regulates its atmospheric CO2 over long timescales. The ocean also stores carbon in another way, through the biological pump. Phytoplankton at the surface use CO2 for photosynthesis, just like land plants. They build their bodies from carbon, and when they die, some of that carbon-rich material sinks to the deep ocean. Bacteria and other organisms consume most of it on the way down, releasing the carbon back as CO2. But some makes it all the way to the ocean floor, where it can be buried in sediments. This transfers carbon from the surface to the deep ocean, where it stays for hundreds or thousands of years before ocean currents eventually bring it back to the surface. Temperature affects how much CO2 the ocean can hold. Cold water dissolves more CO2 than warm water, which is why polar oceans are particularly important for carbon uptake. As seawater cools near the poles, it becomes denser and sinks, carrying dissolved CO2 down into the deep ocean. This is part of the global ocean circulation, sometimes called the ocean conveyor belt, which moves water and dissolved substances around the planet over centuries. The chemistry of carbon in the ocean is a balance, a constant exchange between the atmosphere and the sea, between dissolved forms and solid forms, between surface waters and the deep. The ocean has absorbed about a third of all the CO2 humans have released by burning fossil fuels. Without this ocean uptake, atmospheric CO2 levels would be much higher than they are. The ocean is acting as a buffer, a chemical sink that moderates the rate of change in the atmosphere. But this comes at a cost. The more CO2 the ocean absorbs, the more acidic it becomes, and this affects the chemistry of shell formation. Organisms that build calcium carbonate structures find it harder to do so in more acidic water. The chemical equilibrium shifts, making carbonate ions less available. This is already affecting coral reefs, shellfish, and plankton, organisms that form the base of ocean food webs. The chemistry that helps moderate atmospheric CO2 is the same chemistry that threatens these creatures. A planetary scale reaction with consequences we're only beginning to understand. The ocean stores carbon in shells that eventually become limestone. Deep underground, that same limestone can be carved away by water in a reverse process, creating caves. And in those caves, the dissolved limestone can be redeposited one drop at a time, building stone formations that hang from the ceiling like frozen waterfalls. These are stalactites, and they grow through chemistry so patient it makes rust look fast. The process starts with rain. As rainwater falls through the atmosphere, it absorbs carbon dioxide, becoming slightly acidic, just like the ocean does. When this acidic water seeps into soil, it picks up even more CO2 from decaying plants and breathing roots, becoming more acidic still. This weak carbonic acid is strong enough to slowly dissolve limestone as it percolates down through cracks in the rock. When the water reaches a cave ceiling, it hangs there for a moment as a drop, waiting to fall. In that brief pause, something important happens. The cave air typically contains less CO2 than the water does, so CO2 starts to escape from the water droplet into the air. As CO2 leaves, the carbonic acid becomes less acidic. The water can't hold as much dissolved calcium carbonate anymore, so some of it precipitates out, forming a tiny ring of calcite where the water meets the ceiling. Drop after drop, year after year, this process repeats. Each droplet leaves behind a microscopic amount of calcite before falling to the cave floor. The rings build upon rings, gradually extending downward. The shape is determined by how the water flows. If the water drips straight down, the stalactite grows as a narrow cone or cylinder. If water flows down the outside before dripping off, the stalactite becomes hollow, like a stone straw. The growth happens at the rate of about 1/10 of a millimeter per year in most caves, though it varies with climate and water flow. On the cave floor, where the drops land, another formation grows upward. These are stalagmites, built from the same chemistry but in reverse direction. The drops that fall from the stalactite still contain dissolved calcium carbonate. When they splash on the floor, more CO2 escapes, more calcite precipitates out. Over thousands of years, the stalagmite rises while the stalactite descends. Sometimes they meet in the middle, forming a column that connects floor to ceiling, a stone pillar created by dripping water. The chemistry is elegantly simple. calcium carbonate dissolves in acidic water. That acidic water drips into a cave where CO2 can escape. As CO2 escapes, the solution becomes less acidic and can't hold as much dissolved calcium carbonate. The calcium carbonate precipitates out as calcite crystal. It's the same compound as limestone, just rearranged one molecule at a time into these dramatic shapes. Temperature and humidity affect the growth rate. In wetter climates, with more vegetation, there's more CO2 in the soil water, so more limestone dissolves, and more calcite gets deposited in caves. In drier conditions, the process slows. Climate changes leave traces in the growth rings of stalactites. Much like tree rings, a record of wetter and drier periods preserved in stone. Scientists can date these layers and reconstruct past climates by studying the chemistry of the calcite. The formations can take extraordinary shapes. Flowstones look like frozen waterfalls where mineral-rich water flowed down walls. Draperies form thin, wavy sheets where water seeped along slanted ceilings. Helictites twist and curl in defiance of gravity, growing sideways or even upward because capillary forces and crystal structure override the pull of gravity. All of these forms emerge from the same basic chemistry of calcium carbonate precipitation, just expressed in different ways depending on local conditions. Inside each stalactite is a record of time. The layers of calcite preserve information about the water chemistry at the moment they formed. Trace elements incorporated into the crystal, the ratios of oxygen isotopes, even trapped bubbles of ancient air. By drilling cores from stalactites and analyzing the chemistry layer by layer, scientists can look back tens of thousands of years, reading Earth's history, written in cave formations that grew one drop at a time. Stalactites build up over thousands of years, one molecule at a time. Stars build elements over millions or billions of years, one fusion reaction at a time. And when massive stars die, they create nearly all the heavy elements in the universe in a matter of seconds, through nuclear reactions so violent they outshine entire galaxies. This stellar chemistry is where everything around you came from, including the atoms in your own body. Stars begin their lives fusing hydrogen into helium. This is the reaction that powers the sun and most of the stars you see at night. 4 hydrogen nuclei combine to make one helium nucleus, and the small difference in mass gets released as enormous amounts of energy, according to Einstein's equation. This energy pushes outward, balancing the star's gravity, trying to pull it inward. The star reaches equilibrium, burning hydrogen steadily for billions of years. But eventually, the hydrogen in the core runs out. For stars like the Sun, that's nearly the end of the story. The core contracts and heats up, fusing the helium into carbon and oxygen. The outer layers expand and cool, turning the star into a red giant. Then, those outer layers blow off gently into space, leaving behind a white dwarf core that slowly cools over billions of years. Not dramatic, but peaceful. Massive stars, those with more than about 8 times the Sun's mass, have a very different fate. When they exhaust their hydrogen, they contract and heat up enough to fuse helium. When the helium runs out, they fuse carbon, then neon, then oxygen, then silicon. Each stage happens faster than the last because the heavier elements require higher temperatures to fuse, and each stage produces less energy per reaction. The star becomes like an onion, with layers of different elements fusing at different depths, all happening at the same time. The silicon fusion stage, the the final one, lasts only about a day. It produces iron, and iron is where fusion stops being energy positive. Fusing iron into heavier elements requires energy input rather than releasing energy. The star has been balancing gravity with fusion energy, but now the core is filling up with iron, an element that won't fuse. When the iron core reaches a critical mass, about 1.5 times the mass of the Sun, it collapses in less than a second. The collapse is catastrophic. The core falls inward at 1/4 of the speed of light, compressing to incredible densities. Protons and electrons get crushed together, forming neutrons and releasing neutrinos that escape at near light speed. The collapse stops abruptly when the core becomes so dense that neutrons can't be compressed any further. The infalling material bounces off this neutron core and explodes outward. This is a supernova, one of the most energetic events in the universe. In that explosion, in those few seconds of unimaginable temperatures and pressures, elements heavier than iron get created. Gold, platinum, uranium, all the elements that can't be made by normal stellar fusion are forged in supernovae. Neutrons flood the environment, bombarding lighter elements and building them up into heavier ones through rapid neutron capture. This is called the R process, and it's responsible for about half of all elements heavier than iron. The explosion blows these newly created elements out into space at thousands of kilometers per second. They mix with the interstellar gas and dust, enriching it with heavy elements. Billions of years later, some of that enriched gas collapses to form new stars and planets. This is how Earth formed, from the debris of dead stars, a collection of atoms forged in ancient supernova and stellar cores. The calcium in your bones was made in a dying star. The iron in your blood was created in a supernova explosion. The carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, all of it was cooked in stellar furnaces and scattered into space when those stars died. You are literally made of stardust, assembled from atoms that experienced the most extreme chemistry possible, nuclear fusion and explosive synthesis in the hearts of dying stars. Every element in your body, heavier than hydrogen, has a cosmic origin, a history written in the nuclear reactions of stars that lived and died long before the Sun existed. From the explosion of dying stars to the quiet breath you're taking right now, we've traveled through scales of chemistry that span from the cosmic to the cellular. And what becomes clear through all of it is that chemical reactions are not separate from life. They are life. They're not something happening in laboratories or in distant stars. They're the fundamental process by which the universe changes, evolves, and maintains itself. Every reaction we've explored shares something in common. Atoms don't disappear, they just rearrange. Energy flows from one form to another. What seems like transformation is really just matter finding new configurations, new partnerships, new ways of being stable in a changing environment. The iron that rusts was always going to find oxygen eventually. The glucose you metabolize was always going to break down and release its stored energy. The water vapor was always going to condense when the temperature dropped. Chemistry is the universe's way of settling into balance, over and over again. And the timescales are what make it so calming to contemplate. Some reactions happen in nanoseconds, like the signals crossing between your neurons. Others take centuries, like the carbonation of concrete or the growth of stalactites. Still others take billions of years, like the fusion in stellar cores. but all of them are patient in their own way. None of them can be rushed beyond their natural rate. The atoms will rearrange when conditions are right, not before, not after. There's a deep patience in chemistry, an acceptance of the pace that physical laws allow. Your body knows this patience intimately. Right now, as you rest, chemical reactions are happening at exactly the speed they need to happen. Your cells are making ATP at the rate your tissues require it. Your neurons are adjusting their connections based on what you experience today. Your digestive system is breaking down food in a sequence that's been perfected over millions of years of evolution. None of it rushed, none of it forced, all of it flowing at the natural pace of molecular interactions. The same is true of the larger world. Trees are slowly preparing for seasonal changes through the patient breakdown and synthesis of molecules. Concrete structures are continuing to cure, gaining strength year by year. Fruit is ripening on branches, ethylene triggering cascades of reactions that transform texture and flavor. The ocean is absorbing carbon dioxide, molecule by molecule, moderating atmospheric changes. Stalactites are growing in darkness, one drop at a time. All of this is chemistry, all of it happening whether we watch or not. Even your thoughts right now, the processing of these words, the gradual settling into relaxation, are chemical. Neurotransmitters are crossing synapses. Ion channels are opening and closing. Proteins are being made and broken down. The feeling of calm that might be developing is itself a chemical state, particular patterns of neural activity supported by specific molecular configurations. You don't have to understand the chemistry to experience it. You just have to let it happen, which it will regardless. This is perhaps the most comforting realization of all. The chemistry that sustains you doesn't need your attention or effort. It continues in sleep, in rest, in moments of stillness. The reactions that keep you alive are automatic, reliable, ancient. They've been running in some form for billions of years, passed down through countless generations of life, refined and perfected. All you have to do is rest and allow them to continue their work, as they always have, as they always will, patient and persistent and perfect in their execution. So let yourself settle into that knowledge. Let the chemistry of sleep begin its work, slowing your thoughts, relaxing your muscles, shifting your brain into patterns that allow for rest and restoration. These are chemical processes too, as natural as rust forming or bread rising or stars fusing hydrogen. They happen on their own schedule, at their own pace. Your only job is to create the conditions and then allow the chemistry to unfold. Close your eyes, breathe slowly, and trust that the same patient chemistry that builds stalactites and ripens fruit and maintains the carbon cycle will carry you gently into sleep, one molecular rearrangement at a time, until tomorrow. If you found peace in these chemical truths, please take a moment to like this video and subscribe to the channel. There are more quiet scientific stories waiting for you, more gentle explorations of the natural world to help you find rest. Thank you for being here tonight. Sleep well.